Example 6 discusses a physics kind of application of derivatives and antiderivatives, and it has to do with position, acceleration, and velocity. So before I get into how to solve the problem, let's take a look at some concepts related to this. So in physics, the position function is typically called s of t. I'm not sure why they call it s of t, but that's what they use. Velocity is called v of t, and acceleration is typically called a of t. Okay. We were supposed to have gone over this, but we skipped the section that's relevant, so that's why I'm kind of discussing this with you guys right now. Okay. Now, according to physics classes, if you have the position function and you want the velocity, then all you have to do is take the derivative. The derivative of position gives you velocity. Now, if you have velocity and you want acceleration, then what you want to do is take another derivative. So in fact, what this means is that the position is related somehow to acceleration is somehow related to velocity, and so on and so forth. As a matter of fact, the acceleration is the second derivative of the position, but it's the first derivative of velocity. Okay. Now, suppose that you have somehow figured out that the acceleration is a random number in a problem. How can you go backwards from here? How can you go from acceleration back to velocity? If you have an acceleration function, you just take the antiderivative and it gets the velocity. Now, if you have the velocity and you want the position, all you have to do is, again, do another antiderivative. Okay. So by doing a couple of derivatives, you can go from position to acceleration. And by doing antiderivatives, you can go from acceleration back to position. So let's take a look now at example number 6. It says, neglecting air resistance, the motion of an object moving vertically near Earth's surface is determined by the acceleration due to gravity, which is approximately 9.8 meters per second squared. So this is just basically saying that as you are sitting on the chair or as you're moving, on planet Earth, you're experiencing some gravity pull, and the gravity is pulling you at 9.8 meters per second squared. Now, suppose that a stone is thrown vertically upwards at t equals 0 with a velocity of 40 meters per second from the edge of a cliff that is 100 meters above a river. So let's make a graph. So here's what the graph is going to look like. You're standing right there on top of the cliff, and you're going to throw a stone vertically up. It's going to come up, and then it's going to come back down. Okay. And obviously, when you throw it up, it's going to have initial speed, and the speed at the beginning of the experiment when you launch it is 40 meters per second. So we don't know if that's realistic or not, but who cares? It's just you threw the rock in the air, it went up, and then whatever goes up has to come back down. Okay. So at time 0, the speed was 40 meters per second, and we know that the cliff is 100 meters above the water. So this cliff is 100 meters above the water. So from the river to where you're standing, that's 100 meters. Okay, so far so good? So now the question is, what's the velocity function, v of t, of the object or the rock or whatever? And the hint is that the acceleration is negative 9.8. So the solution is going to look something like this. Earlier we said that if you have the acceleration and you want the velocity, all you have to do is take the antiderivative. So that's what I'm going to do in my case. I'm going to write down, since you gave me the acceleration and you want the velocity, I'm going to give you the velocity by doing the antiderivative of the acceleration. And everything is happening with respect to time, dt. So in other terms, if you want the velocity function, what you want to do is take the antiderivative of negative 9.8 dt. And earlier we said that the antiderivative of a number is that number times the variable of the problem. So whatever the variable of the problem is, in this case it's t, plus the constant c, where c is just some real value. Okay, so this is technically the answer, except it's pretty terrible answer. I mean, I'm not telling you what c is, so you have no clue what the function really looks like. So this is the reason why they had told us the initial velocity. They had told us that at the beginning of the experiment, at time equal to 0, the initial speed of the rock was 40 meters per second. Okay, why would I need this? Well, if I knew that t is 0 and I knew that the outcome is 40, then I'll be able to determine what c is. So all I have to do is take my equation, negative 9.8 times t plus c, and make it all equal to 40 when I plug in 0. So I plugged in 0, and I saw that the outcome was 40. So solve the equation for c. 9.8 times 0 is going to be 0, so that means that c is in fact 40. So if c is 40, then finally we can say that the velocity equation is negative 9.8 t plus 40. So this is the equation that tells me the speed of the rock at any moment in time. So if I want to know how fast the rock was going when it left my hand, I just put t equal to 0 here and I get 40 at the end, which was the initial velocity. If I want to know how fast the rock is going after 1 second, I just put 1 in there and I will say, you know, negative 9.8 plus 40, roughly speaking, let's say 30 meters per second. So it's slowed down because, you know, it's been traveling up and gravity is doing its thing, and, you know, the rock obviously is going to slow down. So that's the end of part 1. Now in part 2 of the question, it says find the position of the object or the rock or whatever. And again, keep in mind that the time cannot be negative. That's why they're saying t greater than or equal to 0. So again, just remember that if you have the velocity, then you want the position. All you have to do is do the antiderivative of velocity to get your position. Okay, so in other terms, I want the position right here, so my solution should look something like this. Since I want the position, I'm going to say s of t is equal to the antiderivative of the velocity function with respect to t. And keep in mind that in part 1, we discovered that the velocity is negative 9.8 t plus 40. So we have to antidifferentiate that with respect to t. So in other terms, we'll have to do the antiderivative for 9.8 t dt and the antiderivative of 40 dt, which, by the way, this equals to negative 9.8 t squared divided by 2 plus 40 t plus some random c, where c is just some constant. We don't really care about it, it's just some real number. Okay, so that's technically the solution. But again, this is a terrible, terrible answer because we don't know what c is, so it's a useless function. So let's go back to the original problem and ask ourselves, do we have any information that relates to position about this object that we're working with? Well, we know that when it left your hand, it was 100 meters above the ground because you're standing on top of the cliff and you're kind of like launching it from the cliff. So it's like, roughly speaking, let's say 100 meters. So that tells me that now at time 0, at the moment of launch, the position of the rock at 0 was 100 meters. So in other terms, I know that negative 9.8 divided by 2 times 0 squared plus 40 times 0 plus c should add up to 100. Okay, the position is 100 at the moment of launch. Okay, so this tells me now that c should be pretty much 100. Okay, so let's put everything together and say, so finally the answer is that the position function is negative 9.8 divided by 2, which is negative 4.9, and then t squared plus 40t plus the 100. So this function will basically determine where the rock is at any moment in time, including at the time of launch. So if you replace t with 0, you'll find out that the number is going to be 100, which tells you that at the moment of launch, your rock was 100 feet above the ground. Okay. So part 3 says find the maximum height of the object above the river. So what's the maximum height of the rock? So from the top to the bottom. So the maximum height happens right here, and at that moment in time, the velocity is equal to 0. Not the velocity of 0. This is saying the velocity has to be equal to 0. So at the moment when you're highest, that's the moment where you don't have any more speed. Then your rock is going to start coming back down. So we're going to take the velocity equation, which was negative 9.8 t plus 40, and solve it for 0. So at max height, the velocity function will equal to 0 because you're not moving anymore. That's when you reach the maximum height. So in other terms, negative 9.8 t plus 40 has to add up to 0. And so that means that 40 is equal to negative 9.8 moves over, we get 9.8 t, and then divide by 9.8. So t is going to be 40 divided by 9.8. Let's find out what that number is. Okay, so 40 divided by 9.8 is going to be 4.08, and then a bunch of other numbers. Let's just round it to decimal places, and 4.08, and then seconds. So roughly speaking, let's say 4 seconds. Okay, and the last question says, at what speed does the object strike the river? So the speed of the impact at the river. Since our reference for the distance was the river, when you strike the river, your height is going to be basically 0. Okay, when the object strikes the river, so when the object strikes the river, the position is equal to 0. So now I'm just going to write down the position function and make it all equal to 0. So by solving this problem, I'm going to end up finding a time. And once I know what the time is, I'm going to put it into the velocity equation to get the speed or the velocity, basically. Okay. Now to solve this equation is going to be a little bit difficult, so I'm going to use a quadratic formula, negative b plus or minus the whole thing. So the a is going to be negative 4.9, the b is going to be 40, and the c is going to be 100. Okay, and I'm going to be using the formula which says that dt should be negative b plus or minus square root of b squared minus 4ac, all divided by 2a. So I would recommend that you do that also on your paper, and I'm just going to give you the final answer here. So the solutions I received were negative 2.006 and then 10.170. Okay, obviously time cannot be negative, so I'm going to ignore the negative amount, and that leaves me with 10.170. So roughly speaking, 10 seconds. So at this point in time, I'm going to try to find out what the speed is. And so all I have to do is go back to the velocity function, which we got over here, and plug in 10 into that to get the amount. Okay, so the velocity is going to be velocity of 10 seconds is going to be negative 9.8 times 10 plus 40. And let's put that in a calculator. And the answer is going to be negative 58. And the units were meters per second. Okay, so why is the amount negative? The amount is negative because now we're going against, in the direction against how it was launched. So we're going down instead of going up. So that's the reason why it's negative. And the speed is 58 meters per second. So I hope you enjoyed. It's the end of the section.